All right, good morning, good morning. All right, good morning, good morning. Okay, but for the sake of time, I'm gonna go ahead and get started. I think there's a good amount of students that have logged in, so we'll move forward. All right, so I just wanted to use this slide at first to remind everyone that we're currently in chapter 6. We're dealing with a class of molecules known as alkyl halides, right? Can you guys see my mouse? Should I change to a laser pointer? All right, so we're dealing with alkyl halides, and we're dealing with a class of reactions that are known as nucleophilic substitutions. All right. Okay, let me let some people in the class right quick. So let's move. I'm gonna skip some of these slides. We talked about a lot of this already. And let's kind of start up again with how do you prepare alkyl halides? All right. Alkyl halides are prepared from halogenation reactions. And specifically, they're prepared from free radical halogenations. All right, this is chapter 4 information, right? So we need a halogen that's going to homolytically cleave into a two halogen radicals that's going to undergo a hydrogen extraction step, and then that radical could rearrange if it needs to, if there's some type of pi bond nearby or a phenyl ring. And then at the end, we're going to terminate to generate our halogenated product. All right. So keep in mind what a free radical halogenation is. You guys had a quiz on that. And also you want to keep in mind what an allylic halogenation is, right? Where there's a double bond present, and that leads also to mixtures of compounds. But typically you want to draw the major product if, I guess if in cases I don't ask for it, you want to draw the major. But if I ask for anything else, be prepared for that. All right, bromination is highly selective here. There's some things in chapter 4 that I come back to at the end, which is talking about the energetics of reactions. So there's some fundamental stuff there that we haven't talked about yet, but that will come up to reveal that brominations are more selective than chlorinations. We'll talk about that chemistry a little bit later once we get done with some of the basic stuff here. So the first example here, if I have chlorine with light or any type of energy, I'm gonna do a chlorination. I'm gonna replace one of the hydrogens with a chlorine. The same thing in this case here, I will replace this tertiary hydrogen with a bromine. We know we get 90% of that because the radical that forms is the more stable radical than taking from one of those methyl positions, all right? The allylic positions are one away from a carbon. I'm sorry, one away from a pi bond. I'm so sorry, or one away from a double bond. All right, those reagents, those hydrogens are very selective, are very easily removed. All right, through to resonance, and a lot of times we get the allylic brominated product. However, there is a reagent that specializes in that. We're going to cover that here shortly. Here's the mechanism. Once you form your bromine radical from your homolytic cleavage, you're going to be able to extract the hydrogen. You're going to leave behind a carbon radical that terminates with Br radical to form the final product. All right, keep in mind what the textbook is doing sometimes is completely different than what I like for you guys to do. So for your termination step, I'm asking that you take your carbon radical and the Br radical to terminate. If you look what the textbook did, this is not termination, but they did another what step here? A propagation, because they form another radical. All right. So the steps that I gave you guys are the ones that are going to lead to that initiation, propagation, and termination step. Anything else will be incorrect for this course because this is another propagation step. It's not the step that I wanted you guys to use to form the product. All right. So the reagent that specializes in doing allylic brominations, an MBS, we talked about this. So whenever you have MBS, be prepared to halogenate at an allylic position. All right. We're not going to talk more about that. We did an example almost very similar to this, to where we get two potential products because of this potential allylic shift that's going to occur. So obviously we can tell that all of these methyl groups are identical. However, we can put a a bromine at this carbon due to the allylic shift. All right. You guys had a mechanism question on your quiz to where you needed to showcase how that bromine was getting brominated through the mechanism, curved arrows. All right. So I will send a key to that. For the ones that I have graded, there was a lot of people that missed that stuff, but I haven't been able to see the recent ones that have been completed recently. All right. So let's talk about some reactions of alkyl halides. All right. The first reaction that you guys are getting familiar with now is the nucleophilic substitution. What happens? I have a carbon halide bond and I have a nucleophile around, and this nucleophile is going to substitute itself in place of the bromine. And this halogen becomes a leaving group and it will leave off the molecule that's sitting in solution, right? So this carbon halogen bond is replaced by a carbon nucleophile bond, right? The second reaction that happens to alkyl halides is eliminations. And the big difference is that now I need a base. A base is going to pull a hydrogen from a neighboring or from the carbon neighboring the one that has a halide, right? All right, the electrons are going to fall to make a carbon-carbon double bond, and you kick off your leaving group. So now you have a carbon-carbon double bond, and you have your halogen left off, right? So the way I like to think about these two reactions are that they're just on the same coin, just opposite sides, right? So this could be the head size, this could be the tail size. Very similar type of processes, just the opposite of each other, right? I can substitute or I can eliminate. We're going to talk about eliminations on Monday, right? So we know there's two types of substitutions. There's the SN2 type, all right? The SN2 has your nucleophile attacking from the back and your leaving group is going to leave, all right? For the most part, this is kind of what this slide is trying to show. Let's talk a little bit more about the mechanism here. All right, again, we're going to use a double-headed arrow. We're going to have our nucleophile attacking from the back and our leaving group leaving, all right? Now, the transition state here has all atoms involved. So the nucleophile and the leaving group with your alkyl halide are all involved in the transition state. We call this transition state a bimolecular type of system where both the alkyl halide and the nucleophile are important in understanding of the reaction, right? So the kinetics of this reaction is dependent upon both the concentration of the alkyl halide and the concentration of the nucleophile. All right, this is a concerted reaction. All new bonds forming and all bonds or O bonds breaking occur at the same time. That's the most important thing here, all right? Everything happens in one sequence. This is how this reaction is typically known and thought of, right? So if you look at the energy diagram here, the transition state is here, and you have your product being lower in energy than that. We're going to come back and talk about these energy profiles and kind of what all this stuff means and why this is important. But The biggest thing to think about here is the fact that this transition state helps us to determine that the steps or the way you draw the mechanism is everything happening at once. All right, that's the key thing to think about. As us as growing chemists, we need to know how does this work in solution. Does the nucleophile attack, or does the leaving group leave first, then the nucleophile attack, right? So we were able to see this information by studying the kinetics of the reaction. Okay. All right, this is a good slide that kind of showcases some of the utility of SN2 reactions. I can take any alkyl halide and convert to all these different functional groups, right? So I can take an alkyl bromide, and if I react it with an iodine, I can make an alkyl halide. All right, in this case, an alkyl iodine. I can take an alkyl halide, react it with hydroxide, and make an alcohol. I can react it with an alkoxide and make an ether. All right, I can do the same thing with this diol. I can make this diol anion to make a diol, or the diol ether anion to make it diol ether. I can take ammonia to make an ammonium salt, an azide to make a carbon azide substrate. I can take this achillidine. This is a type of metal achillidine to make an alkyne. I can take a nitrile, or in the case here, like a lot of people like to call these cyanols type of salts to make a nitrile. I can take a carboxylate salt and make an ester, or I can take a phosphine type of, in a lot of cases, these are just free phosphine to make a phosphonium salt. So you got to get a good way to say that these compounds are very versatile for functional group interconversions, right? I can take an alkyl halide and make all these potential products, which are very, very useful for us synthetically. Okay, so for the SN2, we're saying that we talked about this already in class, but let's kind of use this slide to just kind of double back, or to double our understanding of this fact that the stronger the nucleophile, the better things are going to be for an SN2. So we want to try to be able to understand when we are reacting with a strong nucleophile. And typically, the way that we look at these are by the charges, right? So atoms that have a formal negative charge are going to be classically considered strong. Everything that does not will be in this moderate level. And things that are kind of have electron withdrawing atoms, or in this case here, atoms that are extremely electronegative, are being the weak ends here, right? So for the most part, for this course, if there's a full negative charge, that will always indicate a strong nucleophile. Anything that doesn't have that full negative will kind of fall in the range of being mild to weak, right? So I think everyone is comfortable with that. But SN2 love strong nucleophiles. The better the nucleophile, the better the reaction. Okay, we're going to come back to this term, the difference between being basic and being nucleophilic. There's a very fine line between the two. However, I think this is better taught when we talk about eliminations, because to do elimination, we need a base. But to do substitutions, we need nucleophiles. So this is giving you guys a clue. A lot of the reagents that could be nucleophiles can also be what now? Bases, right? I've been using stuff like sodium hydroxide for our nucleophile reactions, but those compounds are really known as bases. So a lot of times there's multiple ways these things can react. We'll talk about some of the tricks that we use to really ensure that a compound is either acting as a nucleophile or acting as a base, right? And a convenient strategy that I use in this course is that I would say that the reagent over the arrow should be considered as a base, or I might say the reagent over the arrow should be considered as a nucleophile. And that would tell you either to do a substitution or an elimination. We'll talk about those examples a little bit later. Okay, so the next things is that we want to have a clue about the trends in nucleophilicity. All right, so that means that if I had to rank nucleophiles, what could I do? So the first clue is if a nucleophile is negatively charged versus the neutral component, the negatively charged nucleophile will always be the stronger. So we look at OH versus H2O, or SH versus H2S, or NH2 minus versus NH3. All of the negative charge anions are better nucleophiles than its neutral component, all right, or counterpart. All right, let's look at the next trend for trends in nucleophilicity. All right, nucleophilicity is going to decrease from left to right. What does that really mean? I'm going to decrease from left to right. What am I trying to say here? Any clue for anyone? Okay, let's look at this one. This first example is a bad one. Is again, sometimes the people that make these slides are not chemists, but we'll come back to this trend here. This trend is better explaining the next one. But let's look at Se, selenium, sulfur, oxygen. And I don't have a periodic table to describe right now. But if we had to look at this, these are all in the same column, right? They're just below each other. Are you guys comfortable with that so far? Is that yes, no?
Yes.
Okay, good, good. So that means that there's probably some atomic size that's influencing things here. We're going to talk about this shortly. So the trend is that the larger the atom, and that's with all things common. So what needs to be common is that these need to all have that negative charge, right? So they all have a negative charge. So if they all carry negative charge, and I'm just larger, all right, I'm going to be a better nucleophile than something that's smaller. And basically, that just kind of comes from a basic understanding of like nucleophiles need room to react. And the larger I make my room, the better possibility I have to attacking you, right? So there's like a difference between getting hit by an SUV or getting hit by a Mini Cooper, a little small car, right? The bigger car is going to do more damage, right? And nucleophiles need to approach a electrophilic carbon. So the bigger I am, the better chance I'm going to have to make bonds than something that's smaller, right? Now this left to right trend comes up here. If I look at the fact nitrogen here with a negative charge is a better nucleophile than fluorine. All right, so that's going left to right. That's moving away from electronegativity. So if I'm more electropositive, I'm a better nucleophile. And the way that we think about this is this: electronegative atoms hold tight to electrons. If I hold tight to electrons, I'm not going to participate in being a nucleophile, right? Nucleophiles are seeking electrophiles. They are willing to make bonds. They're willing to use their electrons to do work. So if I'm more electronegative, I hold tighter on to those bonds, electrons, than something that's not. So the trend goes in the opposite direction of electronegativity. The least electronegative, the more nucleophilic. We look at nitrogen and oxygen, both neutral. So ammonium and water. Who's better? Nitrogen. Why? Is less electronegative than oxygen. The same thing here. Well, this is I got phosphorus and I got sulfur. They're both on that third row, right? But who's more electronegative? Sulfur. So sulfur will be weaker than phosphorus, right? So up top here, this is all size. So the larger atom iodine is a better nucleophile than fluorine. Selenium is better than oxygen, and phosphorus is better than nitrogen. Or we would say it's bigger, so it's better. So the next term that comes up is this fancy term that's called polarizability. Polarizability just means that if I have a large orbital, I'm able to kind of spread my electrons better over that area. So typically you need to be bigger, further away from the nucleus so that there's not as much nuclear attraction and your electrons become very flexible. And because my electrons are flexible, and the term that they like to say here is polarizable, I have a better opportunity to kind of make bonds. But when I'm small and I'm closer to the nucleus, so that means that I have more nuclear charge, I'm kind of a hard ball. I'm not flexible. And hard balls don't have an opportunity to really be able to adapt to make bonds. And so they're kind of slower when they make bonds. So this hard small type of atoms are not as polarizable. They're not the best nucleophile. However, these large atoms that are kind of soft can kind of do a better job of making bonds, and they're going to be better nucleophiles. Okay. Any questions so far over the trends? Yes, no. You guys have these slides. I think you guys can follow slides. Okay. So this question came up last class, maybe 2 classes ago, and I wasn't able to get to it. I'm finally able to get around to it now. Is this effect of protic solvents, all right? And this is leading us to think about, why do these nucleophiles pop off the molecule, right? And the reason is this solvate or solvating effect, or you want to say the solvent effects. If you look at fluorine minus here, if it fell off this molecule, it will be solvated by all of these solvent molecules. And again, this solvent molecule is protic, right? That means there are H's here. And so it's hydrogen bonding with this fluorine. And so if this needed to be as a nucleophile that's kind of being drawn here, this is not a super, super good nucleophile, because solvent is all around and kind of interacting with things, right? And the same thing what happened to this iodine or this leaving group here. All these solvent molecules will be bonding to it, and then it will have a higher propensity to fall off the molecule, okay? So this trend is really trying to show, first, is that the nucleophilicity of a nucleophile is going to not be as good as it could be if it's in very protic solvents. Right? We know about the aprotic solvents, and they're going to prefer to do SN2 reactions. Right? They don't have hydrogen bonds to participate. All right, crown ethers, we don't really talk too much about this, but this is a great thing to think about. Crown ethers are present to kind of keep things separated. So crown ethers really are specializing in kind of chelating to cations from salts. And so it leaves a free anion, and that makes a nucleophile super strong. So if we do have a crown ether present, this nucleophile is really negatively charged. It's almost naked. There's nothing around. There's no positive cation around. So this has the full opportunity to act as a nucleophile. All right. And these are the tricks that people do to really ensure that reactions are working properly. All right, let's talk about the leaving group ability. And so we do know that whatever get kicks off of your alkyl halide is a leaving group. Typically, leaving groups need to have the ability to stabilize a negative charge. So being electron negative or having resonance would really be great for a leaving group. So if you look at the potential leaving groups here, chlorine, bromine, iodine, these are atoms. They're electronegative. They like to have a negative charge. The sulfonate, the sulfate, and the phosphate have these oxygen double bond structures, right? And so they have the ability to delocalize negative charges to resonance. And so they make themselves to be very good nucleophile. Water and alcohols and things like that, these typically can leave, but they need to have a positive charge. We'll see different systems here a little bit later, right? So leaving group ability really is depending on when you come off, how stable are you once you leave the molecule? And you need to be electronegative or have resonance to be a good leaving group. If you don't have those effects, you're probably going to be a nucleophile. You're going to add right back. Okay, so we talked about this already. When it comes to an SN2 reaction, methyl primary, secondary alkyl halides are best, but no tertiary alkyl halide can do an SN2 reaction. And the reason is this right here. This is a great slide here. So if you look at this carbon in black is the carbon we need to reach, right? So the first structure here is a primary alkyl halide. This is a secondary alkyl halide. And the last here is a tertiary alkyl halide, all right? Again, the carbon in black is what we need to reach, all right? The nucleophile can easily reach in an SN2 reaction, the primary alkyl halide and the secondary alkyl halide. I see the black carbon. But in the third tertiary, do you see any of the black carbon present? You don't, right? So that means that I can't attack from the back to kick off the leaving group. So tertiary alkyl halides cannot do SN2 reactions. Hope that explains things there. This is just kind of telling you the rates of reactions. The methyl is like super fast to react, and this tertiary never reacts. All right. If I went to this series here, right, the primary N-butyl system is faster than this neopentyl system. Right. So stereochemistry SN2, we talked about that before. That's just kind of explaining the fact that a nucleophile will attack and the stereochemistry will be inverted. Let's take a look at that really quickly. Again, this is showing that inverted from an umbrella. This is showing the transition state. I don't think there's a good slide that I like to show this. We'll have to do this in person to kind of just show some reactions where the stereochemistry has changed. But for the most part, you guys should know that there's an attack from the back and the stereochemistry change. I started off here with the S stereocenter. So this is S bromobutane. And when I form my product, I now have the R stereocenter. So this is R butanol, right? So I went from S to R because I inverted the stereocenter. All right, SN1 reactions. We said this is a unimolecular nucleophilic substitution. The rate of this reaction is only dependent on the concentration of the alkyl halide. And we are learning that we get racemic products, all right? This second point is very important, all right? A carbon cation intermediate is necessary and needed for these reactions, right? There's no way we can get around that. Okay, so let's look at the mechanism of this steps for SN1. First, the leaving group leaves to form a carbon cation, and we know that we have to beware of what with carbon cations, any potential rearrangements. There's 4 ways that a carbon cation can rearrange, right? Once I form a carbon cation and arrange myself to the most stable conformation, or not conformation, but the most stable state I can be in, then my nucleophile will attack and I will form my product. Because carbon cations are sp2 and flat, sp2 hybridized and flat structures, I get racemic mixtures, right? The nucleophile equally attached from the top and from the bottom. All right, that's a unique feature of forming a carbon cation. This is why we receive racemic products. All right, so the rate determining step in any SN1 mechanism is the ability to form this carbon cation. All right, this is why the rate of the reaction depends on this. All right, so this is going through the mechanism here. First step, I form a carbon cation here. There's no rearrangement, so now my alcohol attacks, and I still have this oxygen with a plus. So that means my third step has to be what? I need to have my base remove that hydrogen, and this is just acid-base chemistry to generate my final product. Keep in mind, all products and organic chemistry at this point, sophomore level organic chemistry, should have no charges in your final products. All right. This protonated system here, I don't need to see, but your final product should have no charges. If you draw a structure that has a charge, most likely there's an H that could be removed. So please deprotonate that system to generate your final product. Okay, we'll come back to these energy diagrams a little bit later, but this lets you know that there's 2 potential steps here. I need to form that carbon cation, then I need to be able to attack it, right? And I have this intermediate here that's depending on the ability to form a carbon cation. Okay. So carbon cations are the complete opposites of SN2. The tertiary alkyl halide is better than the primary, and the methyl never reacts unless there's some type of potential rearrangement. But in this case here, there's nothing else there, so this is why methyl halides never undergo an SN1. All right. The better the leaving group, the better the reaction is going to be here. All right. It doesn't matter how strong your nucleophile is. It's all about how easy can that leaving group fall off to affect the rate. All right. We talked about this as well. Why tertiary alkyl halides are better than the rest, because of the fact that neighboring carbons can donate electrons in. We call this effect here this hyperconjugation whenever there's an sp3 hybridized orbital donating into a p. typically there has to be p orbitals and lone pairs for a normal conjugation. Whenever I use an hybridized orbital, we call that hyperconjugation. Right. All right. Solvation here is very, very important. All right. If a solvent can help solvate, and that just means dissolve these anions, that's going to cause this to form or these things to break apart. And this is the best slide to really show the fact that leaving groups leave because of this. This carbon cation becomes solvated and the anion becomes solvated. This is all facilitated by the solvent. So polar protic solvents are best for this because they have the ability to solvate these things, and that causes your intermediates to be formed. All right, this is a great slide to show that this carbon that's sp2 hybridized has equal opportunities to be attacked from the top in the bottom lobe, and in doing so, you generate both enantiomers. Up top, I have the S stereocenter, and I started off with the S stereocenter here. On the bottom, I have the R stereocenter, and this is the inverted center. But from this intermediate, I always generate both. Okay. This is why I have a racemic mixture of compounds. All right, I'm not gonna, this is the same slide showcasing the stability of carbon cations. The stereochemistry of an SN1, we talked about that already. We're gonna get both enantiomers. And this is showing the potential of rearrangements. Okay, so the bromine is here. It could leave and form a carbon cation here, and my nucleophile could attack at that position to give me this. However, I have another product that's formed where now this H has the nucleophile, and this came from being rearranged, right? So there's two of the rearrangements presented here. A hydride shift or a methyl shift can occur to generate carbon cations or to rearrange carbon cations, and they're going to always rearrange to form a more stable carbon cation. Right, so up here, this is a methyl shift that occurred. They don't have an example of a hydride shift. That's fine. They don't do the other two, the resonance or the ring expansion. But we know that there's four ways to rearrange a carbon cation. All right, so this is like the ending slide here before we get into some problems today, is that SN2 prefers things that are least substituted, methyl, primary, secondary alkyl halides, while the SN1 prefers tertiary and secondary alkyl halides, all right? So that's a good clue for determining which mechanism type there with the alkyl halide. The second clue is the nucleophile. For SN2, you always need a strong nucleophile. There's no way to do an SN2 without a strong. And SN1 can work with weak, but also they can work with strong nucleophiles as well, right? And you want to also remember that the nucleophile could also be the solvent. We call that solvolysis when that happens. All right, for SN2, polar aprotic solvents are needed. For SN1, I need a polar protic solvent because it will help solvate the anions, the carbon cation and the halide anion. The kinetics are determined from the concentration of the alkyl halide and nucleophile for SN2, but only for the alkyl halide for SN1. I get inverted stereochemistry. For SN2, I always get, for SN2, I get inverted stereochemistry. For SN1, I get the racemic products. SN2 never rearranged, but SN1s could potentially rearrange depending on the scenario. Okay, so is everyone getting comfortable, I'm hoping, with these characteristics between SN1 and SN2 reactions? All right. What I wanted to do next was talk a little bit about the quiz that you guys had earlier. Let's rank these really quickly. If you had to rank these radicals, what is this first radical ranking? Anyone in class? That's more welcome to speak up. What do you call that first left-hand radical?
Tertiary.
Tertiary.
Okay. Is there any other information from that one?
It's Benzylic
Benzylic.
tertiary.
Okay. So tertiary benzylic looks good to me for the first one. What about the second one? What would you call that one?
Primary. Secondary benzylic.
Secondary
Secondary and what else?
Benzylic.
benzylic.
Benzylic. That sounds like
How is it benzylic? I thought that had to be a ring.
needs to be next to a phenyl ring, right? pH stands for phenyl. Does that help?
Yes.
Okay, can we go to the third one? What's going on with the third structure?
It's tertiary.
So that one's tertiary. Any other information there?
Benzylic and allylic.
Yep, that one's benzylic and allylic. And the last one is what type?
Tertiary and then the triply
Double.
benzylic.
It's
Yeah,
double benzylic.
that one's tertiary and doubly benzylic. All right, so these are the answers here for those systems. Somebody needs to get that into the class. All right, so the first one here is tertiary. I went ahead and counted off the 3 potential carbons here, but it's also in benzylic because it's one away from this phenyl ring. So this is tertiary benzylic. The second one is secondary benzylic. So these are the 2 carbons that are next to the carbon that has a radical. And again, I have a phenyl ring, so that's benzylic. So this is secondary benzylic. The third structure here is tertiary again. There's 3 carbons near that carbon. It's allylic because it's next to a pi or a double bond, and is next to a ring, so which is a phenyl ring here. So this is allylic benzylic. And the last structure here has 2 phenyl rings and a regular carbon. So it is tertiary, but it's doubly benzylic. All right, so that's good. So the first skill you guys want to keep in mind is being able to classify the radical. All right, there's some other things that I'm seeing. Also, I think I received some messages on Teams that I wanted to make sure people are kind of clear with. What is a mechanism? All right, I want to make sure you guys are. I should have been no S there, but what is a mechanism? All right, that's got a mixed spell. So sorry, but a mechanism, IMS, got my letters transposed here, is a curved arrow that shows the flow of electrons for product formation. All right. So when I ask for a mechanism, I'm asking for the detailed steps. Can you show me the flow of electrons through curved arrows to get to the product? All right. That's completely different than when I ask for a predictive product. Predictive product, you need to know, you need to have knowledge of the reaction mechanism, but you don't have to show the mechanism. Just give me the product. All right. So there's a lot of times that I just ask for the product, and you have to do all this stuff mentally or on paper on the side if you need to. And there's steps where I'm asking for the detailed mechanism, right? And typically, I can't ask a lot of these. It takes a lot of time for you guys to draw those. So I can assess if you know the mechanism by if you draw the right product. But a lot of times I will ask for at least one case where you have to show me the details of a mechanism. So hoping everybody is comfortable with that. All right, another big thing here that was kind of issue that I want to make sure I clarify today is the difference between a double-headed and a single-headed arrow. All right, single-headed arrows are always used when I'm doing reactions with radicals. All right, a single-headed arrow describes the flow of one electron. All right, so it's very important to be able to use the correct arrow there. A double-headed arrow is used when I'm describing the movement of 2 electrons. And this is common. The 2-electron process is common for most mechanisms. So for substitutions and for eliminations and for all the other chemistry that's coming up as well, all the mechanisms here are always double-headed. Single-headed arrows are only used for radicals, all right? So for the mechanism on the quiz, you needed to use a single-headed arrow. I've already graded the ones and I indicated if you didn't use it or not. I'll try to finish the rest of the grading later today so you guys know to be aware of that. On this exam, that's a skill that you have to make sure you have down. For the mechanisms that I'm asking you for, are you using the right arrow? And that shows back to me that there's some level of understanding of the chemistry, okay? So let me go live and let's go ahead and draw the mechanism for the reaction that I asked you guys for today. Where is it? Give me one sec. this mechanism here. So I asked for this mechanism. Let's go ahead and break this down. I wanted to do this live. So what's the first step in this mechanism? Should be a what step? Initiation step, right? All right. So how do I initiate my radical?
Separate the electrons in the bromine.
Yeah. I'm gonna have a homolytic cleavage at the bromines, right? So that
Mhm.
means that one electron goes to each atom in that bond, right? Am I using the right arrows here? Double-headed arrows, by the way. I'm not. They should all be single-headed. This is going to be a pain, looks like a little bit. All right, I just want to color these red because I think that makes a contrast. All right, and please, I didn't have enough time to fix the settings. I'm going to have to play around with things to get these to look a little bit better. But these are single-headed arrows here, all right? So again, this is a homolytic cleavage. And light will facilitate this. So all I need is a little light. We're going to talk about some other things that also form radicals. And you guys are going to learn that hydrogen peroxide also does that. And this is why when you buy hydrogen peroxide, it's in a black or brown bottle because you don't want it to break apart yet. All right. So when I do that, I get 2 of bromine radicals in my first step. All right. I'm hoping everybody is feeling comfortable with that. All right. The next step is that I'm going to need one of those radicals to react with the system here. All right. Again, I can only pull hydrogens from atoms involved in single bonds, right? So in this case here, none of the H's on the phenylrenes can come off. There's no H's here. There's one H here, but it's involved in a double bond. And these H's are the only potential ones that can be extracted. So I'm going to draw one of these H's here. And my next step is going to be a hydrogen extraction step. All right. So this radical is going to extract the hydrogen. So that means the H in its one electron is going to move over. And the other electron in this bond is going to reside on the carbon. And once I do this step, I'm going to generate this radical here, right? All right. Now, this radical does not lead to my final product. If I terminate here, I'll just have a bromine here. And this is the step I didn't see from a lot of people, all right? So I'm going to try to make sure that I specify it here. So this is the hydrogen extraction. Right? And this step is a propagation step. So I'm going to put prop up top as well. Right? Because I start with a radical and I end with a radical here, right? So this is my propagation step. All right, the next step that has to happen here is a allylic shift, and that's just a resonance type of thing, all right? So this single electron and one of the electrons in this pi bond is going to move over here, and the other one is going to reside back here. All right, these are not the best of arrows. I just don't want to spend a lot of time today on this because I did cover this already. But for the most part, those arrows are kind of showing how things should be moving. I have to make my own arrows to get it the way I want it to look. All right, so this step here is describing the allylic shift. Use the wrong arrow here. Sorry, this is a resonance step. So through resonance, and that's that 1-2-3 system again, right? So atom 1 had the radical. Now atom 3 is going to have the radical, and atoms 1 and 2 will have that double bond. All right, so this is a resonance. But we like to call this the allylic shift. Okay, now that I have my indicated radical, all right, and you guys know why this happens, right? What type of radical is this one? This is a primary allylic radical, right? And it goes, when it does the allylic shift, to a what type of radical? Any takers? Right, so it goes from something that's just plain old primary allylic, because it's next to double bond, to a system now that's tertiary allylic, because it's next to a double bond, and doubly benzylic, right? So this is an extremely stable radical here. All right, all that happens in my last step is that now I need my BR radical, my second one. Actually, let's do this. Let's just make this all second. Step. All right, these two things are going to happen in my termination step. That would have been a good arrow to use. All right, these two things are going to meet. All right, and they're going to form what? They're going to form my final product, right? So now I have a what type of bond present? A BR bond. Okay. So I'm hoping that everyone is starting to get comfortable here to do this reaction or to do the mechanism here. There's a couple main steps that we needed to have down. All right, let's review really quickly. All right, we need to do an initiation step that had a homolytic cleavage to give us 2 bromine radicals. One bromine radical is going to do a hydrogen extraction to form this, I guess, our primary allylic radical. This radical can do an allylic shift through resonance to form a tertiary allylic doubly benzylic radical that terminates with the second bromine to generate our final product, right? So be prepared to kind of be able to think along these lines, right? You want to be comfortable with thinking about mechanisms and how to draw the flow of electrons for these processes.
Okay, Dr. Cooper.
Go ahead.
So from the initial problem, we're supposed to be able to recognize that we don't go ahead and put that BR where it's supposed to be because, well, where you put the H, we don't put it where the BR is because we have to do resonance.
Yep. Like when I saw this, that carbon is involved in a double bond, but over here it's not. So it reveals that there was some type of movement of that double bond in the formation of that product.
Okay.
So not seeing that just is not thinking about it clearly, but it's definitely shown here that that step had to be shown in the mechanism to get the bromine there.
Okay.
Does that answer the question?
It does.
Okay, good. All right, let's kind of move into now me just giving you guys some random problems. All right, so I want to see, man, God, class is almost over. All right, in the last amount of time that we have, can you guys give me the major product from these reactions? Give me 1 sec to draw everything out. I don't know why these things are so small today. Yeah, these are the wrong settings. I don't know what the settings are set right now. Not the settings I want to go with. All right, I gotta make things that big. This will be a CM 16. All right, I guess we gotta do 2 at a time because of the time I'm in. All right, I'll get you guys to start thinking about these while I'm making the other. Can you guys, in your private settings, try to draw the major products from these? And these are all going to be substitution class reactions. All right, so I'll give some instructions here. I'm gonna draw this one out. Boy, so let me do what I need to do here. All right, this is the last one right here. All right, can we determine the major products from these reactions? All right, let's take our time. I'll give you guys a few seconds to work with the first three, I guess. All right, these are all substitution reactions. Can you tell me the major product from the first two? And because of the sake of time, I'm gonna move through this as quickly as I can. So I'll just kind of talk it through it. So the first thing I need to do to be able to think about drawing major products, and I need to think about mentally. Again, I'm not asking for the mechanism here. I'm just asking for the product. But to be able to draw the product, I need to know the mechanism. All right. And I can gain clues about the mechanism by looking at all components. So what type of alkyl halide am I dealing with? What would you say here? All right. Sake of time, I'm going to say this is a primary alkyl halide, right? What type of solvent am I dealing with? Polar aprotic. And if you have another class and I'm saying you got to go, I'm going to keep the recording on to go through all this. Please feel free to try to come back in or try to watch this later. And my nucleophile here is strong, right? It's strong because I have a carbon, which is a non-metal, and a metal lithium bond, right? And that's going to make a ionic bond. All right, so the ionic bond reveals that there's going to be a negative charge. All right, so in this case here, my mechanism is going to be a SN2 type, right? I have a polar aprotic solvent. Typically, solvent dominates these type of things, but primary alkyl halide and a strong nucleophile also reinforces all that information. So this is going to be the SN2 type. So my product is just going to have my nucleophile coming in from the back. So my answer here is going to be this right here. All right. So I'm going to replace the carbon bromine bond with a carbon methyl bond, right? That's the nucleophile. The byproduct, if this helps students, I'll do it, is lithium bromide. All right. So the lithium and the bromide are going to form lithium bromide as the final product, right? We can talk about the mechanism at a different time. All right. My next reaction has the same alkyl halide, which is primary. But this time I only have one thing over the arrow. So I know that this is a Savolysis reaction, right? Where my nucleophile and my solvent are the same thing. All right. My solvent is polar aprotic. I'm sorry, polar protic. That makes this mechanism type which type? This is an SN1. Am I talking to myself or just everyone just quiet just because it's convenient? I've done that before where no one was in class. Hello. Oh, okay. Okay. Thank you. Okay. No one is saying anything. Can you guys hear me in Teams?
Yes.
Oh, okay. Great. Great. I'm getting ready to say I gotta check and see. All right. So in this case here, I'm going to end up getting a SN1 product. I did the wrong thing here. All right. I'm going to form a carbon cation here that's going to be next to. I'm going to try my best to show as much of this as I can. A ring, right? And we always say that we need to check for rearrangements here, right? So this is going to rearrange itself. All right, I need to use smaller arrows here. All right, again, that's primary. I'm next to a ring. There's no hydride, there's no methyl. So the only thing I do is a ring expansion here. And that will give me a 5-member ring. Oh, sorry. I'll have an alpha group there, and now my carbon cation is there. Right. This is going to react to form my final product. It's going to be this right here. All right. Let's move the alpha group down a little bit. Can't believe we went to the same spot. What is going on with ChemDraw today? All right, this is going to be my final product. All right, I got this product via a ring expansion. Right? So you want to be on the lookout again mentally if you need to try to do the mechanism in your head, and that will probably be a big help in trying to see all the potential things that can happen. All right, I'm gonna come back to that later to try to clean it up. All right, let's move to the next one here. I just need to put this in gray. It just helps me not to see. All right, so I have this bromide, and this bromide will be classified as a secondary alkyl halide. I have NaOMe. Again, that's an ionic compound. So this indicates a strong solvent. And I have methanol that has that H on it. So I know that these conditions are polar protic solvent. And this is set up nicely for an SN1. So what I have to see here is that the first step is going to generate a carbon cation, right? I'm always SN1 now. And I need to check, can this carbon cation rearrange? And hopefully you guys can see that it can. All right, and this is going to rearrange via a hydride shift. I'm going to draw the H in here. This hydride is going to move over here. I'm going to generate now this carbon cation. My plus is now there. And my final product from this reaction is going to have my OMe here. I'm going to make that 16 in size. And that's going to be that product. All right, let's put all this in gray. If you got any questions, you can speak up, but I know you guys are just trying to get through this because of the time. I got office hours on Monday. I'm going to have a session on Sunday. I'll see you guys information about that as soon as I know how my Sunday is going to be. So that's probably Saturday that you'll get an email from me. All right, I got the same alkyl halide again this time. Also secondary, right? I also still have that strong nucleophile, but my solvent this time is what type of solvent? Polar aprotic solvent, right? So now I'm forcing the reaction conditions to stay what? As an SN2 reaction, right? So now this is just plain old SN2, and my nucleophile is going to come in from the back. So instead of having a wedge, I'm going to have a dash O ME. Right, and that's going to be my final product. All right, up top for this carbon and for that carbon, they came by the SN1, which have nucleophilic attack from the top and the bottom. However, this carbon is not chiral because of two methyl groups. This carbon has two carbons in that side, two carbons in that side. They're completely identical. So again, those two carbons are achiral, so I don't have to draw any wedges and dashes off those carbons. But this one does, and I don't make a racemic mixture. I only make one, and that's the inverted system, right? So up top here, I wanted to write this in if I can. I got the second product via a hydride shift. Right, so this is a hydride shift here. All right, let's look at this I'm sorry, I got not my last, but close to the end here, this next example. This alkyl halide is tertiary. I'm hoping everybody is getting comfortable with that. Right, the carbon that has the halide here has 1, 2, and 3 carbons. So that's a tertiary alkyl halide. All right, my nucleophile here is strong. There's a metal carbon bond there. So that's a strong bond because it's ionic. There'll be a negative charge here, a positive charge on the sodium. And my solvent in acetone is also polar aprotic, right? So my conditions here are favoring exclusively an SN2, right? So the product here is no reaction, right? Why don't I get a reaction here? Why is this no reaction, right? And the reason here is that I can never do a substitution at a tertiary alkyl halide, all right? So no SN2 substitution at a tertiary alkyl halide, right? Nucleophile cannot approach electrophilic carbon. Right, so keep that in mind. That was a question to make sure you guys understood what can happen and what can happen in these type of reactions. Let me make that a little bit smaller to fit in there. All right. So this is a no reaction here. All right, let's move down to this case here, right? What type of alkyl halide is this? All right. This is known as a vinyl halide because it's directly attached to that double bond there, right? So that's a little unique, right? My solvent here is still, I'm sorry, not my solvent, my nucleophile is still strong. There's a metal, non-metal bond. And my solvent, however, is polar protic, not aprotic. There's an acidic H here. So I have all these things set up. So my reaction conditions are favoring an SN1 mechanism here, right? Again, the solvent dominates. Strong can work with any type of solvent, but in this case here, this is going to be SN1. The answer here again is no reaction, right? The reasoning here is that you cannot do any substitution at a vinyl halide, SN1 or SN2. So there's no possible substitution. When I mean that, that could mean SN1 or SN2 at vinyl or aryl halides. All right, so keep that in mind that if I have any halide attached to a carbon and a double bond, they cannot participate in SN1 or SN2 reactions. All right, that's different chemistry they can do, but the chemistry you guys do not know yet. So right now for substitutions, it does not react. All right, in the last case, what's going on here? I have a primary this is just regular primary alkyl halide. And I have only a solvent again, so that means my solvent is the nucleophile and the solvent, right? So as a nucleophile, this is weak, and as a solvent, this is polar aprotic. So my reaction conditions are also favoring a SN1 mechanism. Right. So typically SN1 cannot happen at primary alkyl halides except if there's some type of rearrangement or resonance. So let's take a look at the carbon cation that forms in the first step. So my leaving group has to leave. And I'm going to generate this carbon cation. And this carbon cation luckily has right next door to it a double bond, right? Or a pi system. And that's going to afford me an opportunity to I probably need a closer one. Oh, boy. To do resonance here, right? So from the resonance, I'm going to generate now this carbon cation. Now my nucleophile can react at that carbon cation. So I went from something that was primary allylic, something now that is tertiary allylic carbon cation. So maybe I'll write the word carbon cation here. Make sure everyone got the right intermediate describe. This is the same thing here. This is a primary allylic carbon cation. Right, so my final product is going to be where my nucleophile attacks the plus is at, and that's going to lead to OET here. Can you give me 1 sec, Dr. Sagapi? Yeah, I'm still in class. It's just, we just went over extremely long. And I have an OET here. I'm going to change the font to 16. And again, this just looks weird. What happened? Yeah, it's not reading that right. Sorry about that. All right, and again, I don't have to show any wedges or dashes because the carbon that gained the nucleophile is achiral. Right, so I kind of did that deliberately today, so I didn't have to draw multiple products. But these are all the potential answers to all these systems. All right, so you guys do have the skills to kind of work around all this. It just takes a little bit of practice, maybe, to feel comfortable. But I'm confident that you guys can do it, right? So there's a list of practice problems to try. I highly recommend to try those. And if you need to reach me, you can this week. I'm so sorry that, next week. I'm so sorry that this week was a little tough. I just had a lot of little things in the background that I had to complete. So I just wasn't available as much as I would like to be, but I will be next week. Everything is back to normal. Your exam twos, I'm almost done. I'm so sorry I couldn't finish them all last night, so I should be done with them this weekend. But if you need to converse with me, I might be free for a little while. Actually, somebody just came by my office. I need to run and take care of that. So just try to send me an email, and I'll try to let you know when I'm free today to kind of talk. If you can wait until Sunday, I can also talk with you after we do that review session about your exams. And you guys are more than welcome to come by Monday to pick them up. All right, if you took them in person. All right, if there's no more questions, I'm going to go ahead and stop the recording.